Hi, I'm going to talk today about section 7.5, which is what to do when you're presented with an integral and you don't know what to approach, what method to use to approach the integral. Well, we only have a certain number of tools and we have to figure out which tool is to be applied first and so on. So let me get started. So we have the following methods we've introduced so far. So technique number one is what you might call use substitutions. That's the first substitution you learned. So that's a very, very broad tool, and it usually won't work right away. So another technique we introduce is partial fractions. And if the integrand has a rational function, the technique of partial fractions should probably be used. So so you have integration by parts. We also have trig substitutions. And that's basically, then we have also trigonometric trig integrals themselves. So these are basically all the techniques we have so far. Now there are some other integrals which you can approach with some other types of substitutions. They're U substitutions, but you might not know what U would be offhand. But let's start off with something simple. Let's start off with the following problem. So I'm choosing an exercise out of the section. So let's look at the following integral. The integral of cosine of x dx over 1 minus sine x. So if you look at this, you might think this is some sort of trigonometric integral, but it actually is more easily handled by a U substitution. We can let U equal 1 minus sine of x. So then du is cosine of x dx. And so this becomes, we have a cosine x dx in the numerator, so we have du over u, and this becomes ln absolute value of u plus c, but u is 1 minus sine x. So this does the problem right away. Very simple. Okay, so that was just a warm up. Let's try something more complicated. Let's try something like this. And this is actually from the section. It's a square root of 1 minus x over 1 plus x, which you can think of dx. Now you can think of the square root of 1 minus x over 1 plus x as the square root of 1 minus x over the square root of 1 plus x. Now, you could try doing a substitution, u equals the entire integram, but that's going to be a very messy thing. It turns out in this case, it's easier to rationalize the denominator to get rid of the square root. So what I mean by that is the square root of 1 minus x over the square root of 1 plus x is equal to itself times the number 1 written out in the following funny way, square root of 1 plus x over the square root of 1 plus x. Oops, yeah, that's it. So if I do that, what happens? I get that the numerator becomes the square root of 1 minus x squared, and the denominator becomes 1 plus x. Okay. So I don't know what this buys us actually. So let me go back and try something else. I'm going to change the expression in the following way. I'm going to think of this as the square root of 1 minus x over the square root of 1 plus x. And then I'm going to multiply both top and bottom by the square root of 1 minus x. And then this becomes 1 minus x in the numerator, and the bottom is the square root of 1 minus x squared. Okay, so therefore the integral becomes the integral of 1 minus x dx over the square root of 1 minus x squared, which is the same thing. I'm going to break it up into two different fractions, 1 over the square root of the square root of 1 minus x squared. Okay, and the other piece is minus x dx over the square root of 1 minus x squared. Okay, now the first of these integrals is just the arc sine, the inverse sine function, because the derivative of inverse sine is 1 over the square root of 1 minus x squared. So this is the inverse sine of x. And what's the second integral? Well, we've done this integral actually already several times. It's a u substitution. And I'm going to spare you the details because you should be able to do this. You're going to let u equal 1 minus x squared. Then 1 half du is dx. And if you do that, and I'm going to skip the step, this becomes the square root of 1 minus x squared. And then is the answer. In fact, the derivative of this expression is the integrand, so it is the right answer. And then we have to add a c. So I skipped a step, but this is the idea. So what do we take away from this? Sometimes you might have to just play around a bit. And in this case, I did not rationalize the denominator. I changed it into something which I could integrate by some algebraic manipulation. Okay, let's do another one. So let's try this problem, problem 3. The integral of dx over x times the square root of x minus 1. Now, the book says when you see a square root and what's not in the square root is not of the form where you can do one of those trig substitutions, it sometimes is helpful to just set u equal to the entire square root. So in this case, we're going to let u be the square root of x minus 1. So then what's du? Du is equal to 1 half x minus 1 to the minus 1 half dx, which is the same as 1 half dx over the square root of x minus 1. Okay. So therefore, if I multiply both sides by 2 du is equal to dx over the square root of x minus 1. Now I have that in the integrand already. I just have to account for the x, but what is x? Well, if I square both sides of the expression, I get u squared is x minus 1, so x is equal to 1 plus u squared, let's say. Okay, so what do we get? Oops. So we get that this is the integral of so the dx over the square root of x minus 1 is a 2 du, and what's left over is the x, which is 1 plus u squared. Okay. But of course, if we bring the 2 out, this is twice du over the 1 plus u squared, and that integral is the arctangent of u. But now we have to go back, and then we have to add a c, of course. And we have to go back and express this in terms of x. So this is twice arctangent the square root of x minus 1 plus c. So that's that integral. So when you have a square root, sometimes you can try and just let u be the square root of x minus 1, and hopefully that will help you. It might not, but sometimes it will. Okay, so what problem is this? This is problem 4, I guess I'm doing now. So this one is from the text. It's the square root of 1 plus e to the x dx. And now you might say let u be, because of what happened last time, let u equal the square root of 1 plus e to the x. If you try that, you end up with a mess. It's messy and it won't go anywhere, so I'm not going to do that. So I'm going to try something else. There are not many things to try, right? So we could try letting u equal e to the x. Let's see where that gets us. Then du is e to the x dx. So what is dx? Dx is, since e to the x is u, du over u equals dx. So this integral becomes the integral of the square root of 1 plus e to the x is u times dx, which is du over u. Okay, does that buy us anything? Well, now we have something which has a square root, and I think we should try and get rid of the square root by letting v equal the square root of 1 plus u. Why did I use a new variable v? Because I've already used up u. Okay, so what is dv? That's equal to 1/2 1 plus u to the minus 1/2 du. And so let's see how we have to convert this to an integral in terms of v. And so let's do it. So what do we get? So this is the integral of the square root of 1 plus u, but that's v. Oh, notice that this is the same thing as the dv is the same thing as 1/2. So the square root of 1 plus u to the minus 1/2 is actually 1 over v. And so du, and I have to get du by itself, right? So I'm going to get this. So therefore, 2v dv equals du. Okay. So we've taken care of the square root of 1 plus u. That's here. We have to take care of the du, and we have to take care of the u. So let's do that. So the du is 2v dv, and the u, what's u? Well, we can solve for u. If we square both sides and subtract 1, we get u equals v squared minus 1. Okay, so we're going to get v squared minus 1. So what do we get? We get this is the integral of 2v squared dv over v squared minus 1. Okay, so now this is a partial fractions problem now. Okay, so in order for me to do that, I'm going to make some space. Okay, so I'm going to get rid of this stuff here. Oops, let me not do that. Let me first save the screen and then do that. Okay, so we want to consider the partial fractions. That we ought to express the partial fraction of 2v squared over v squared minus 1. Now this has got to be long divided first because the numerator has the same degree as the denominator. And I'm going to work this out myself, and we'll see what we get. So I think this is worked out by myself. I did it before, and I got it's given by 2 plus 1 over v minus 1 plus 1 over v plus 1. You can check that that works. Okay, so therefore this integral is the integral of 2 dv plus the integral of dv over v minus 1 plus the integral of dv over v plus 1. And that gives me 2v plus ln of v minus 1 plus ln absolute value of v plus 1. Okay, great. So I'm going to still need more room, so let me, because I have to convert everything back into x. Okay, but before I do that, there's a plus c here. This is actually equal to 2v. I'm going to combine the v plus 1 and the v minus 1 to get an ln of v squared minus 1 plus c. Okay, so in fact, I don't have to erase yet because u is v squared minus 1, and v is the square root of 1 plus u. So this becomes twice the square root of 1 plus u. That's the first term, 2v. And the second term is ln, absolute value of v squared minus 1, which is u, plus c. Okay, but now we know what u is. In fact, I can write the answer here without erasing anything. The answer is given by substituting the value for u as e to the x. So it's twice the square root of 1 plus e to the x plus ln, absolute value of e to the x. Well, ln of absolute of e to the x is just x plus c. So I could actually rewrite this. It should be rewritten in the simplest form. Plus x plus c. That's the final answer. Okay, so that's the final answer to this problem. Okay, great. So there you have it. Those are some extra problems. The basic theme is if you see a square root, maybe the substitution u equals what's the square root will sometimes get you out of trouble. There's no guarantee, and this is just, I provided you hopefully with a toolbox to which you can approach various integrals. That's basically all. As far as 7.6 goes, I'm not going to cover 7.6 because that shows you how to use an integral table, and frankly, you can just go online instead and use the various tools that are there instead of using an integral table. So I don't think it's actually, I think integral tables are really kind of not used anymore. Okay, so try the extra credit problem. That's actually a very, very long problem that uses every method we've learned so far. Probably takes 3 or 4 pages of calculations and 20 minutes to do. So take care.